However, Mr. Che has agreed to be in here during zero period. I'm going to start it off and then I'm going to leave. He's going to go ahead and miss the meeting and make sure that you guys are able to stay in here and keep working with coffee and donut holes, etc. And then he'll probably kick you guys out at about 1:45, but period 1, kids, you can leave your stuff in here, go grab a drink, go to the restroom, etc. Then the sub's going to come. Does that make sense? So don't make Mr. Che like just wait in here until right before the bell and run over to his room. That's not cool. So I'm having him kick you guys out at 1:45, then the sub will come back. At that point, if one of you doesn't mind being in charge of unplugging my coffee pot, because if it doesn't get unplugged, then it'll turn on the next morning and it'll kind of ruin it. So anybody want to be in charge of unplugging my coffee pot? Patricia, thanks. Just the cord in the back, you're just going to pull it out. Is that cool? You're my hero. And then Naomi will be on the field trip. I'll have someone in like honors pre-cal or regular pre-cal. No, I'll have someone in period 6. They can clean up whatever's left from the zero period trash. Besides that, you guys in class are going to have a work date. Once again, I said, go ahead and make sure you sit with people that you don't mind working with, and you can finish up or go over questions on homework 5.2. That's why it's not due until 6 p.m. So both classes have a chance to have like that work day time. Anyone on the field trip, maybe I'll make it a little bit later so they have a little bit more time when they're at home. But also I have you guys working on due Thursday, section 5.3. I might go ahead and make that one at night too, so that we have class time on Thursday to go over questions also. But remember our calendar. I didn't get to show you a pretty picture of it yesterday, but showing you a nice picture of it today. Here we go. We don't have our test until next Tuesday, which might seem short, except guys, we only have on this test 5.1 to 5.3. We're going to be playing with our review and questions on the review on Friday and on Monday. We have 2 review days. This is going to be our book review going over questions and answers to, and this is going to be our AP review, our free response review. You guys are going to be getting on Thursday your practice test that has some FRQs, and we're going to be kind of working on FRQs Thursday after we go over homework questions. So basically 5.2, 5.3, we're going to see today why I think you can tackle both homeworks by Thursday. And then tomorrow just being a work day as far as you guys just working on those 2 homework assignments. So let's start off in section 5.2. We did already cover this non-forever card because it's not on the AP, which is why I put little parentheses around section 5.2. But sorry, it is going to be important for our homework. But really quickly, before we get into the word problems, which is where you guys can get slowed down a little bit, before we get into the word problems where you can get slowed down a little bit, I am opening up section 5.2 so that we can peek at actual homework questions and see how today is helpful. And that way tomorrow when you guys are trying to work on it together, you can go ahead and even, if you guys don't mind, I'll put a quick note to the sub that I don't mind you guys opening up your phones and accessing YouTube, accessing Google Classroom, because I'm going to do some examples today that will especially help. But ideally, you should work on these things tonight, and then tomorrow in class, you will have already compared what we do today in class to what the book has, ask a couple questions, and my goal is for you guys tomorrow to be working mostly on 5.3 and getting ahead as far as tomorrow night's homework. So that's what my goal is. All right, cool kids. So with that, section 5.2, let's get back into our notes. We were working on this last differential equation yesterday, and you guys are rock stars because we are ahead of period 6, which doesn't happen very often in here. I think my little spiel about people being absent, and I know it's flu season, like you guys can hear my voice. You know that I'm just trying to hang in there and be here every day, even though some people would say I should probably be home. I don't think I'm contagious. Congestion is gross right now. But I get it. So if you're absent, if you're not feeling well, do what I would need to do if I stayed home. Work. Get sleep, get rest, but then when you're awake and when you're alert, try to work. Encourage your friends. Reach out to them, especially if they're sick. Joyce knows it stinks, and trying to catch up stinks. So love on them. But also hang in there yourselves. I know it's hard to come to school when lots of people are gone. So this differential equation, what happened when we multiply by dx? Who didn't belong? The y. But the problem was it wasn't just y. It was grouped together to be 4 minus y. And that's one of the biggest mistakes that people can make in the sense that today is what, guys? The 5th? Yeah. Sorry, trying to get those correction papers copied. End of day. Okay. When we multiply by dx, and this is this is huge, and the ironic thing is, ever since Algebra 1, when I used to teach Algebra 1, I would make a big deal about these parentheses with this kind of problem in mind, which is ironic. Like, I'm totally being like, if you could just get your algebra skills down, you wouldn't be making this mistake in calculus. I know it's silly, but it's important. When you multiply by dx, this is a binomial. It is trapped, and if it's trapped, algebraically, the only way to move the y is to move the entire 4 minus y, which is why I had to move it to the other side. This became a u sub problem, which you guys are going to be working on your u sub as you work on test corrections over the next week and a half. But u equaling 4 minus y, du, I did my u substitution. It led me to an ln, but here's the problem. When I'm solving a differential equation, what am I trying to get by itself? At the very end, what am I trying to get by itself? The y. So if I'm trying to get the y by itself, and if it's trapped in an ln right now, first of all, I moved my negative to the other side. The negative went to the x. Minus c can be plus another arbitrary constant c, or plus a negative that gets absorbed. I had to do e to the power of both sides, and then there's this, just like we saw in the problems before, because of exponent rules, I can make this e to the negative x times e to the c. This can all be absorbed into a new c, so I could make this like a c1, make him a c2. Long story short, I get down to this c e to the negative x. Now comes the little trick at the very end, as far as in your homework. Wait, why are we doing these problems? In your homework, I just said I was going to open up section 5.2. Where does homework start, guys? Yeah, thanks, Patricia. It starts in this section. This section says to do what? Solve the differential equation. What is the very first thing you're going to do every single time? Multiply by dx. Multiply by dx. And so when you multiply by dx, you're going to integrate. Okay, guys, come on. Eyes up here. Eyes up here. Come on, eyes up here. You're going to multiply by dx. You're going to put parentheses whenever you're multiplying. Guys, numbers 1 and 2, do I have to move anything if I multiply by dx? No, all I have to do is integrate. But numbers 3 and 4, if I multiply by dx, what am I going to have to do to the 6 minus y, or the y plus 3? Divide it, just like we're doing right now. So this is like numbers 1 through 10 as far as solving. What are we going to have to do? Oh, wait, y prime. Who's y prime? dy dx, multiply the dx. Oh, he's not going to belong. Oh, he's not going to belong. See what I'm doing? Wait a minute. dy dx. Oh, maybe I have to add, then maybe I have to divide, then maybe I have to dx. So there's going to be some steps. I don't think I gave you tons and tons, but I gave you a few. Section 5.3 is basically just this. That's why I'm thinking you can start 5.3. It's solving differential equations. Not as particular as 5.2, but I put the ... yesterday because we ran out of time. But whenever we have an absolute value, we go to basically plus or minus. In the sense of solving algebraically, we would make a plus equation and a minus equation. And the crazy thing is, because of our c able to be a positive or a negative, in some senses, and maybe we'll get a little more particular as we do AP review, in some senses that plus or minus can be absorbed into that arbitrary constant. So I can kind of say, well, depending on the clue, sometimes it'll be positive, sometimes negative. We can kind of just absorb that plus or minus, and then we can solve for y a couple different ways. We can subtract the 4, divide by a negative, or we can add the y and subtract. Either way, we end up with y equals, add the y, subtract, makes it easier in my brain. And we can get y by itself. Some of you were like, wait, if you're subtracting an arbitrary constant, can't you do a plus? Technically, yes, you kind of can. Because there again, that negative can get absorbed into that arbitrary constant. So that's just kind of giving you some practice as far as doing that first section of homework. But number 1 does have a video attached. Remember, the sad thing is it's one of the most basic ones. But you guys also have odds you can check out on CalcChat. And they should show some work. Maybe not every single thing. Maybe some CalcChat jumps might throw you off. But that should help you out. I did have another example But for our purposes, I'm going to go ahead and skip over that example to get to, here we go, number 26. Yeah, let's get to number 26. Kiddos, if I was to compare this to homework, I would now be, and maybe we could peek at some questions over here, except number 19 has a nice video to go along with it. Rate of change proportional to is very similar to what we did yesterday as far as talking about this proportional wording and how we set up if y's rate is proportional to y's amount and how we solved that. But I did definitely, if I gave you one of those problems, I expected you guys to check out the videos. The videos are very helpful. There's a slope field. Numbers 11 and 12 doesn't have specifically a video. So actually we could go ahead and, for numbers 11 and 12, peek at that one I just skipped. Let me just get rid of him real quick. The wording that could go along with this, kind of comparing it to our homework problems. The rate of change of, I could translate this to say the rate of change of P, technically with respect to T, is directly Y, because it's K times, not K divided by. Directly is K times, not K divided by. Is directly proportional to, this is going to be awkward. I don't really want to make words in that, so I'm just going to do 10 minus T. This could have been the words that led to this differential equation that then they would ask you to solve. So here's a quick example going backwards. Here you see words that you're going to have to go from the words to the differential equation and then try to solve. So I've gone ahead and in this one, number 12, whenever it says rate of change of P with respect to T, that's dB dt, is directly proportional to, I should actually probably put that whole thing, there you go, is directly proportional to, that would be this right here, K times, and then K times what? Well, then we just go ahead and finish it off. Okay? And then once you have that differential equation, that's the hardest part of those next problems. Once you have that equation, then you could go ahead and, just like we saw before, multiply the dt on the other side. On this one, it's not too bad because K is a constant and that's a t, so actually we are totally good to go. There's no other rearrangement necessary. You could go ahead and integrate. But I wanted to show you guys that one just as far as where the differential equation came from. It came from this wording right here. Okay, sorry, that brings us up to number 26, which is super similar, if you guys notice, to right here, these graphs which have the directions of, hey, guess what? These are all exponential swoops. Now, some of them are like vertically, no, none of them are vertically flipped. Some of them are horizontally flipped. But if you remember just the basic CE to the KT, the most basic one is actually just a swoop. There it is, right? But all of these have been changed. Well, that one's been like squished. This one's been like flipped. That one's been squished but kept the same direction. That one's been flipped. But we don't actually have to stress about thinking about what transformations happen. Instead, let's just go ahead and take our equation and say, well, if that's the equation, well, what can we do? Well, if that's the equation that somehow this is exponential decay, technically, because it's going down. Guys, this takes us back to Algebra 1. Algebra 1 said, wait a minute. If you have two different points, can't you go ahead and plug in both points? And say, okay, well, if y is 4 and, well, okay, this is my t, this is my y, t is my x. I plug in 0 for x. And if y is 1/2, when x, which is my t, is 5, Can't I use like, well, maybe not elimination because I can't like subtract, but substitution at least to solve? If I have two equations and two unknowns, that's a system of equations. No big deal. Let's solve this puppy. So if we take this, hold on, what's 1? C equals 4. Haha, I got 1. Well, if C equals 4, can't I go plug it in? So then 1/2 is equal to 4 e to the 5k. How do I solve for k? Not ln yet. That's a good idea, though. What do I need to get rid of first? The 4. So divide by 4, which is multiplying by 1/4. I get 8 is equal to e to the 5k. How do I get rid of e? There you go. See, AJ, I just needed to get e alone first. So I can say 5k is equal to ln of 1/8. So I could say k is equal to ln of 1/8 all divided by 5. That's right. Someone else might say something to the effect of ln of 8 to the -1, which ironically, you could then go ahead and make that ln of 2 to the -3, because 2 cubed and then to the -1, which you could make that -3 ln of 2. There's a lot of different like variations as to what this could look like, and if you were taking like a chem class and they were having you solve, you might have used an equation that got you to a different form, but these are the exact same thing, whether that k or this k. Long story short, as long as you have one of them that's correct, to find the equation that would get you this exact curve, all you'd have to do is plug in your c and then plug in your k in whatever form you want. Now, if you're up here in like an exponent, usually it's kind of messy to write all of that, so maybe I'd write a 1/5 instead, ln of 1/8 times t. That's okay. If you don't like the 1/8, you could do like the 8 to the -1 and make it -1/5 ln of 8. There's a few different ways of writing it, but as long as you have a valid statement, you're okay. You're okay. So far, we're basically just building up to the whole, like, okay, there are harder differential equations. If it's given to us, basically, how do we solve? Move the dx. If we need to, move the y expression, get y's on one side, x's on the other, integrate, try to get y by itself with math. The c is going to sometimes get stuck, especially if you're taking ln on both sides. I apologize, e to both sides. Talking about how wording can be changed or put into differential equations, relationships, and then we can solve. And then zeroing in on, okay, this section 5.2 is all about exponential growth and decay. So let's just talk about the algebraic equation and how he fits all of these different patterns or trends. And then we go to word problem practice. Now, let's check out where homework goes next, because homework is what you guys are going to be working on tonight and in the morning, focusing on this exponential growth guy. And if you guys notice, there are all sorts of different examples. Let me move my book up just a little bit about how this can be explained. Now, not explained, but used. So we have just some equations. That's going to be kind of basic. What's harder is when they start giving you tables. Some of you might recognize some of this stuff kind of from last year, because we actually saw it when we were talking about exponential functions. You guys just weren't having to deal with like derivatives in original functions. It was a bit more basic than that. But these tables are basically saying, hey, radioactive isotopes, there's an application. Radioactive decay, carbon dating, those are both decay, there's an application. Compound interest, there's an application with all this exponential stuff. And it keeps on going, and then it gets to more word problems. Now, I haven't given you everything. I've been very focused on what I have given you. Bacteria growth, that's a huge one as well. You're going to have a few different examples as far as what you're supposed to do. But wording that you're going to see is things to do with initial quantities, half-lives, doubling, amount after some sort of time has passed. Even though all these problems look kind of different, some things will be the same in some way, shape, or form. And the nice thing is they all come back to, in some way, shape, or form, thinking about this card. Thinking about this card, and specifically this equation that we took time to label. Amount after time t, initial, constant of proportionality, which is kind of like a rate, time that is passed. Everything that we just saw has something to plug in. And so basically it's just saying what clues have I been given and how do I use them? What clues have I been given and how do I use them? Now I have different examples here. This one I can go ahead and basically walk you through step by step, like an ABCD sort of thing. But with your guys's, looking at the wording really quickly, I think the wording on yours is actually even a little bit easier than this wording gives you. So let me go ahead and expand all of these and then give a quick blank page to have us look at it. So suppose an initial population of 10,000 bacteria grows exponentially at a rate of 2% per hour. And y equals y of t is the number of bacteria present t hours later. Okay. If we were to write this as a differential equation, and this is what the AP doesn't necessarily require you to do. When you read this wording grows exponentially, we can actually say what the differential equation would look like. And we could say, oh, okay, so y prime is equal to k times y. Now they didn't tell us directly proportional to, but exponential growth is always directly proportional to the rate of y, directly proportional to the amount of y. And we could say our initial clue says that y of 0 is 10,000. This is like an initial value problem that you could have seen on an earlier test, Chapter 4a, Chapter 4b, where they give you the differential equation and they give you an initial amount. They could have also written it, or you could have also written it as dy dt, because we're dealing with time as our x. That's another variation. But the nice thing is if it's exponential growth, true exponential growth, you're not going to have to multiply by dt and integrate. We know what's going to happen. We know we're going to come down to this equation. So that's the cool thing. We can make a huge jump and we can be like, oh, without even integrating, it's exponential growth. Yay, I can use this guy. And more specifically, formula for y of t, we can actually plug in some stuff. Like, for instance, we have a clue of our initial. So you could go ahead and plug in 0 for t and plug in 10,000 for y. But what's going to happen, we can kind of skip ahead based on that yellow box that we did. If we plugged in 10,000 for how much y is present at t equals 0, this will always become 1, and c will always become, in this specific example with exponential growth and decay, c will always become the initial amount. And not just that, we can plug in c is 10,000. But there's another clue in here, right? Grows exponentially is a clue. Initial population of 10,000 is a clue. And then what's the other clue? A rate of 2% per hour. And I said something about the constant rate, or the rate of the constant of proportionality. If it's saying 2% per hour, that means how fast the rate of y growing is increasing at a rate of 2% per hour. So I could actually plug in the k back here when I'm defining the rate, which means I can plug in the k down here as well. Now, they don't always give you that rate of 2% per hour, but when they do, it's kind of nice because I can go ahead and say, sweet. Plugging and chugging, I have my equation. So if they were to ask something like, and in our book it's all in a table, where it's saying things like, hey, I'll give you how much time to double. And that's down here in the second section where we're talking about doubling. I'll give you how much time to double. I'll give you my initial investment. That's my C. I'll give you my annual rate. That's my K. They give you different clues to plug in and different unknowns, and so you solve for what you don't know. Or if they're doing half-life, same thing. They tell you the half-life, and they give you different clues. You fill in what you don't know. Ours is just, this example is just asking it in words instead of a table. But if it says how long, what are we finding, guys? How long, find t. Good. Find t when double. What's doubling? Time is doubling, the rate is doubling, the amount is doubling. Who's doubling? The amount, yeah. So if the bacteria is doubling, doesn't Y stand for the amount? So if it doubles, that means it went from 10,000 to 20,000. So I can say, oh, okay, I just need to find T when Y equals 20,000. Or another way of looking at it is when Y of T in general is equal to double your initial. But in this told us the 10,000, so we could just plug in 20,000. But in a harder problem, if we don't know the original, we could always take what, oh, go look at that yellow box again. The one from yesterday. Didn't I say something about a ratio? Can't I rearrange my equation to have my C actually be on the other side? So I can do my Y of T all over Y sub naught equals e to the kt. If I rearrange that general equation dividing by the Y sub naught, or if it helps you guys, dividing by the C, I can be like the ratio for doubling is going to be 2, which 20,000 over 10,000 would be 2. Or 2 times Y sub naught all over Y sub naught would be 2. But I can go ahead and just set 2 instead of even having to know 10,000, and that double of that is 20,000. 2 equals e to the 0.02 t. And if it was half-life, I could make the ratio equal to a half. Oh, no. 20,000 would go here, and 10,000 would divide. Yeah. So what we have is double what we had. So since it's growing, the ratio would be 2. If it was a half-life, if the 10,000 was becoming 5,000, if it was decaying, then it would be a half. But at this point, I'll just take an ln of both sides, right? So we're playing with some algebra, playing with some inverse operations. T is equal to ln of 2. And guys, you could put that in your calculator, get a decimal, etc., etc., etc. But you would just need to, for my purposes, stick it to the man. Just throw in a label of hours and you're good. It's all about, can you read what they're giving you and plug it in the right place? So even though our AP doesn't require you to have memorized these relationships about exponential growth and half-life and doubling, the idea of reading, finding the clues, plugging in is still important. Letter D, how long? What am I finding? Good. When population of bacteria reaches? When Y of T equals 45,000. So we're getting used to these variables. We're getting used to these quantities. That Y of T is an amount. T is time. And some of the math that comes along with solving for what we're missing. So letter D would be find time. This one, there is no ratio specifically to worry about because they didn't say anything special. It wasn't doubling or halving. So whatever, 45,000, we know it starts at 10,000. We know the rate of growth is 0.02. Guys, you would just very similarly solve for T in hours. So they're giving clues. You're plugging in, and you're solving algebraically, legally, with the calculator getting decimals. Does that kind of make sense? I wouldn't go to a graph, because if you go to a graph, you're going to have to get a window of 45,000. Don't do that. Don't do that. Use your algebra of dividing, taking ln, dividing, etc. Does it get any harder? Well, I don't know. Let's see what changes if we have, E. coli. That's doubling too. Let's go to a half-life problem. Let's go to a half-life problem instead, because we already did a doubling one. We already had a growing one. Let's go to a radioactive decay. This is actually earlier in homework, I think. With this one, and it's kind of like your table at the very beginning of your homework. Polonium-210, would that be an isotope? No, I don't know. I think so. Find an initial value problem. Radioactive decay. Nice thing is, he's actually going to have that same directly proportional to. We could put a negative if you wanted to. But I'm going to show you how you don't actually need to put a negative. The information will kind of work out the negative in and of itself. We know our Y of 0 is equal to 10. Because of that, we could make it a dy dt and multiply and integrate both sides. The nice thing is, though, this entire section is exponential growth and decay, so we can go straight here. You can use the c, you can use the y sub naught, either way. Using our clues, we can plug in pretty quickly in the sense of, well, we can kind of plug in. They didn't give us a percentage for the rate as to how fast it's growing this time. So if I go to plug in, my 10 equals c e to the k times 0. Oh, that's right. Every time my c is going to be my initial. I can come here, but the struggle is, who's k? They didn't give me that percentage rate. I've used this guy. Who haven't I used yet? What does that clue tell me? T. Good. It tells me a T. So I plugged in this guy, my initial, and I was able to get my C, which is good. But then I also need to get a K, so somehow I need to be like, okay, half-life. Half-life. That means the amount of the polonium-210 has cut in half. So two ways of doing it. One way is to make this guy 5 and divide the 10. The other way is that the ratio of y over y sub naught is equal to 1/2, which will be my e to the k t. Oh, wait. Time, I know time. E to the k times how many days? 140. So I can go ahead and take ln of both sides. I can divide by 140. Once again, chemistry might have you memorize another equation, how it's 2 to the negative 1, and then you bring down the negative. Actually, I think chemistry has you do the 1/2 for half-life. 1 over the number of days for the half-life, ln of a half equals your constant of proportionality. But either way, now I finally have my y equals 10e to the 1 over 140 ln of 1/2 t. Whew. And from that equation, what are they going to ask us to do? How many milligrams? Ooh, what are they asking for in letter C? What variable am I solving for in that equation? How many milligrams? Yeah, it's an amount, right? And isn't the amount y? How many milligrams? So find y when, keep translating, not 10, because we're doing days. 70. So can't we just plug and chug and say y of 70 is equal to 10e to the over 140 ln of 1/2 times 70? And then we're just going to label it milligrams and be like, yay, done. Plug and chug to calculate. Technically, that's an expression. Some of you horribly illegal stuff, canceling out e and the ln. You'd have to pull that power up before you do that. And even then, the 70 kind of messes you up there. It's better to plug and chug. But letter D asks something weird. What does letter D ask? How long? So find when 70% of the original sample decays. Does that mean 70% left or 30% is left? 70% decayed away, only 30% is left. So my ratio, like our card tells us, y over y sub naught is going to equal 0.3 or 3/10. What's left is 0.3 or 3/10. Remember, that's when you divide the initial to the other side. So what's left is e to the 1 over 140 ln of 1/2 t. And what are you going to solve for? ln both sides. Find t, and it's going to be in days. Do you guys see how there's a lot of algebra? A lot of reading the words and translating what they're saying, and then trying to plug in what you know to find what you don't know. Does that kind of make sense? So it's I don't know, it's going to feel kind of like a pre-cal lesson in some ways, as long as you, once again, come back to your yellow box, as long as you keep straight what the different variables are. as far as this one is the amount after time has passed. That's the initial amount. That's our rate if they give it to us, but a lot of times they don't, and we have to go find him. And this is the time that has passed. So, and you have your ratio, your rate. If it's a half life, you can make that a half equals. Or if it's doubled, you can make that double equals. Or if they say something like 30% is left or 70% is decayed, so 30% is left equals. That's where you can make a little quick ratio. Now, guys, that's section 5.2. And I know that there are some blank pages, but it's because I was doing them in a really weird way another year. So what on earth is going on in section 5.3? And why do I think you guys can at least together in your groups start it tomorrow? I'm going to go ahead and make the 5.3 homework due Thursday night. Probably around 6 o'clock again, so that we have class time on Thursday. We might kind of make a work day out of Thursday also. Me going over questions on 5.2. Some of you guys just able to work on 5.3 in class. I do have a few extra books up here, kiddos. I'm letting the sub know you can come up and borrow books. You can also maybe bring your book if it's in your locker, etc. But section 5.3, what is different, what is new? Not much. Guess what? You're going to be given differential equations. Guess what you're supposed to do? If needed, rewrite with differentials. And then rearrange. How familiar does this feel? Rearrange so that you can do what? Integrate. Dot, 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 until you get to a place where you need to plug in your clue. You might just see trickier differential equations. The idea of separation of variables is what I've been telling you already. I need to get a function in terms of y on one side with dy, a function in terms of x in the other side with dx. There must be multiplication with the differentials to make that sandwich legal to integrate. You can't be adding a dx or subtracting a dy. It has to be times dy times dx. But as long as my x terms are grouped with a dx, I can integrate. As long as my y terms are grouped with a dy, I can integrate. So basically, it's what legal algebra do you need to do? What legal dividing or subtracting, not forgetting your parentheses, etc., do you need to do in order to be able to integrate? And then you're plugging in clues and finding C's and just seeing what happens. Where does the C get stuck? How do I solve for it? So section 5.2 is very specific after the very first few problems. Exponential growth and decay. You don't even need to integrate a lot. You're just using exponential growth and decay. Then 5.3 says, zoom back out. There are lots of different differential equations. Can you solve them? Okay? So tomorrow in class, work day, bring your book if you have it in your locker. If not, there's going to be 1, 2, 3, 4, 5, 6, 7, 8 different ones up here. Work together to get as many questions answered. And bring those questions to me on Thursday. Sound good? All right. Bye, cool kids. I'll see you later. I know it was